Okay, so let's carry on. We're going to build on the two general facts that we just established for when we add together random variables. And we're going to add a really important element here, which is the key of the central limit theorem. Okay, so again, the central limit theorem applies when we add together or when we take the average, because that involves adding, when we take the average of many independent copies of the same variable. Independent copies of the same variable. For example, you select 100 men and they all have heights that are they're all random variables from the same distribution, right? So suppose you have x1, x2, x3, all the way up to xn. These are n independent copies of the same random variable x. So for example, x might be the height of a random man in the world living today. So let mu x be the mean value. So that would be like the the mean height of one man. Sigma x is the standard deviation of x. Then the sample mean x bar, what that means is it's going to be x1 plus x2 plus x3 all the way up to xn divided by n. Okay, so I'm repeating what was in the box above, but it's just so important. Now, here's the key thing. No matter what the distribution of x is, like x doesn't have to be normal or it could be anything. The two general facts above tell us that the mu x, so the mean of the sample means, is the same thing as mu x. So it's the same as the underlying mean. Now what's that saying? If I go out and I ask 100 men how tall they are, and then I get the average for that, say it's called a survey, I find the average height for those 100 men. That's one sample mean. Imagine I did that every day. So every day I go out and I ask 100 men, how tall are you? And I get a different sample mean every day. And I do that forever. So I have an infinite number of, or just many, many, many different X bar values. What's the average of all those, right? It'll be a little bit different every day. But if I average over all of them, I should just get the height of the average height of a man, right? And that's what I would. Okay, now the sigma squared of x bar, so the variance of x bar is, I'm going to skip the kind of step-by-step thing we did last time. It's going to be the variance of x divided by n. So what that tells us is that sigma of x bar oops, I forgot the bar. Sigma of x bar is the square root of that, which is sigma x over square root of n. And so we call this thing here is sometimes, we could call it the standard deviation of the sample means, standard deviation of the sample means, but it also has a kind of slightly shorter name, which is, it's called the standard error, that's a tough one, standard error of the mean. Now, that's a phrase that it took me forever to remember that phrase because it sounds a little bit vague, but it means exactly this. The standard error of the mean means just this sigma of x bar. Okay, so those are kind of the first, this is set up for the central limit theorem. Now here's the main thing. The central limit tells us that not only do we have these key parameters, we also know the shape. We know the shape of the distribution for x bar, right? Because potentially there's many different distributions with the same mean and the same standard deviation. But the central limit theorem tells us that actually the shape of this distribution. And what do you think it is? It tells us the shape of the distribution for x bar is normal. It's a normal curve, as long as there's two conditions. Well, the first one is if the underlying variable x is itself a normal variable, as in the height examples we did, then x bar will also be normal. That's kind of the easy case. We just did that. The more interesting case, it's more relevant for everyday life, is even if x is not normal, if the sample size x is large enough, so let's say large enough, if the sample size is large enough, then it'll be normal. So the central limit theorem here, it only says that there's some value of n that's large enough, but generally speaking, 30, as long as n is at least 30, that's a kind of rule of thumb. That generally speaking, it turns out that 30 is generally large enough. So this is true even if, oh, I've got my dog here saying hello. Okay, so even if, I should add that this is true even if x is not normal, is not a normal variable. That's the kind of magic of it. Okay, so let's just draw a quick picture of that. So let's say x is some weird distribution like that, right? There's the distribution for x. It's some crazy trimodal thing, right? That's fine. If I take samples, and so let's say its mean value is right here, and its standard deviation is, it's hard to even know where to draw it, but its standard deviation is something like that. If I take samples of size n, which is greater than or equal to 30, then the distribution of x bar looks like this. It's not crazy anymore. It's very well behaved. It's a normal distribution. Let me draw it skinnier so you can get the idea. It's a very rather narrow distribution that's still centered on the same average, same mean, but the sigma here is much smaller. It's the old sigma divided by the square root of n. When you divide by the square root of n, that's going to make it much, that makes sigma x bar much smaller, right? Oops, I'll write that a little more neatly. So for example, let's say it's 100 men, right? I ask 100 men how tall they are. Then the square root of 100 is 10. So that would mean that this new sigma is only a tenth as big. So it's much more focused. Okay, and this is, you might not see it yet, but this is actually, it's like the very center core of this, of statistics, is this fact. That's why it's called the central limit theorem. When we add together multiple copies of the same variable, or I should say when we take the mean of the multiple copies of the same variable, the standard deviation is divided by the square root of n, which means the larger the n is, the narrower the distribution for x bar becomes. And that will have all sorts of helpful practical consequences. All right, so let's do a more concrete example. So we're going to look at this is something we've looked at lots of times, the distribution of household income in the United States from a few years ago. And I'll just remind you, we did look this up, and the mean household income was 72,641, and the standard deviation was 63,000. So let's see, 72.6 would be around somewhere around here, somewhere in this area here. Oops, it's hard to draw a straight line on this tablet. So let's say that's the mu somewhere in the middle, and the sigma is 63, so that would put us down somewhere around 10,000 or so. So the sigma is like this, and then also in this direction. you might say, well, hey, why does it seems to be going beyond the curve, and um, that's okay. It's showing. I mean, these ones are way beyond the curve, right? It's harder to interpret sigma when it's not a normal distribution, but it's giving us the spread. Okay. Now, clearly, the shape of this distribution is not normal, right? It's very skewed to the right. And there's our friend Jeff Bezos sitting in the last class there, 250,000 and over, or like way over. Um, so that long tail is kind of getting squashed into these last two classes. All right, so that's for individuals, right? This is individual households. Let's just add that, individual households. These are the parameters for individual households. Now what if we think of taking samples of 100? So if we take random samples of 100 households, well, let's just boil it right down. If we take 100, it's going to be much less variable than just individual households. Because in a group of 100, yeah, I might have some really large, I might have a Bill Gates or a Jeff Bezos in there, but I'm also going to have 90 regular people and maybe even a few very low income houses. There's probably going to be several very low values to kind of balance out the high value. So when I take the mean of 100, it's going to be closer to the center. So the distribution of x bar, it's going to have a mean value, which is still the same mean value of x as x, which is 72,641. But its standard deviation is going to be the standard deviation of individual households divided by the square root of n, which is 63,400. What's the square root of n? It's square root of 100. Why did I pick 100? Because that makes my life really easy right here. I just have to divide by 10. So now it's just 6,340. So much less spread than for individuals, than for individual households. Right? 10 times less spread. And then here's where the really the magic part happens, that the shape of the distribution for x bar is normal. So we can draw the distribution for x bar. You say, like, how do mathematicians know that? Like, how do they know that the shape is going to be normal? Well, first of all, part of it is that all they can tell us is that the shape is normal if you add together sufficiently many households. In theory, you might even need more than 100. You might need to add 1,000,000 households together, and then at that point, there's going to be very little variation, right? But the rule of thumb, in regular life, it happens to be around 30. It's kind of a rule of thumb. So even to prove that for the mathematicians to prove that there's some value of n beyond which the shape is normal, even that requires a huge amount of theoretical development. Oh, she's finally comfortable enough in the new house to come say hi. Oh, there we go. Okay, so what is the mean? The mean value of x bar was 72,651. And now the new spread here is 6,340. So why don't we figure out a couple of these? Actually, we're going to do that on the next page. So I won't figure out anything further. But we have to say why. How do I know it's normal? Is it because the underlying variable is normal? No. That was the first possibility. Or is it that n is sufficiently large? As in, i.e., n is greater than or equal to 30. Well, yes, that's the one, right? That's it. Because here we did n is 100, and 100 is definitely larger than 30, right? Okay, so if I drew, if I drew it on here, the distribution for x bar on here would be something like this. It's even skinnier than that. It's going to be like, because by the time I get $6,000 is like not just a bit more than one of these classes. So it'll be like this. So this is like the distribution for x bar. It sort of shrink wraps onto the mean. The more n, the higher n is, the tighter it becomes to the mean. In fact, if I let n, might be a little bit much for you, but if I let n be the entire population, 320 million or whatever, then the mean of that sample is definitely going to be exactly the mean. It'll be perfectly flat. Okay. All right, so let's do a practical example here. I mean, we're going to continue this in a practical manner. So again, let x be the income of a random US household, a random individual US household. What is the probability that that individual household is less than 65,000? So this is actually hard to answer. 35,000. It's hard to answer. You can't answer it in a theoretical way. What you have to do is just look at the numbers. So what is the probability that x is less than 35,000? Well, 35,000 would be all of these classes, right? These are the ones up to, oops, I went too far. This would be the last one here. These are the ones that are less than 35,000. So what are the numbers here? So I would need to add up, what's the probability? So let's write it out like this. Under 5,000, 5,000 to 10,000. So it's the probability that x is less than 5,000 plus the probability that x is greater than or equal to 5,000 but less than 10,000 plus 10,000 up to 15,000. And then I'll say dot, 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 because I don't want to write all of them. The last one will be 30,000 to less than 35,000. And what I'm going to do is I'm just going to estimate it from the graph. So I need to do, this one is about 3%, 3%, 5, 5, 5, 5, 5, right? It's roughly right. 3%, 3%, this is the percentage right here. 3, 3, 5, 5, 5, 5, 5. So what is that? 3%, 3%. How many fives was it? I think it was 5 fives. 5 fives? Yeah. So that would be 25 plus 6, 31%. 31% of all US households are earning less than 35,000 from the chart, from the histogram. Now, we didn't need the central limit theorem to answer that, right? Next one we do. Now, what if I take x bar being the mean income for 100 households? Now, what is the probability that the mean is less than 35,000? Well, it's going to be a lot smaller, right? Because look at our distribution for x bar. X bar doesn't want to be down below 35,000. X bar wants to be close to the mean, 72,000. So it's going to be very unlikely that X bar is as low as 35,000. Much less likely. So let's actually calculate this. So we know that X follows a normal distribution with with the parameters mu x bar is, it was 72, I forget now, 72,641. And sigma of x bar is, I think I can remember this, it was 6,340. So that means, so get your Excel out right here because we're almost ready to use Excel. The probability that x bar is less than 35,000. How do we do that with Excel? I'm just giving you a little drawing here. So it's I want to know the area to the left of 35,000. There's the mean. And there's the sigma. So how do we do that? It's norm dot dist, right? Norm distribution, 35,000. And then I have to give it the mean value. Should move this over. What's the mean value going to be? The mean value is, so it's right there, 72,6. I better not use commas because commas mean something different. And I better not use the dollar signs either. And then, so it goes mean, sigma, and then cumulative. So do we want cumulative or non-cumulative? Yes, cumulative, right? Yes, cumulative. And let's see, what does Excel tell me here? So I have to start it up. I didn't do this before, sorry. All right, so let's make that bigger. Okay, so I need norm.dist of 35,000, 7172, I can't remember, I've written it so many times, 641, 6340, and true. So remember, this should be a pretty low probability, right? Pretty low. It's extremely low. 1.45 times 10 to the minus 9. 1.45 times 10 to the minus 9. So it's extremely, extremely tiny. As in, we'd have to do this survey 1 billion times, because it's 10 to the minus 9, or like maybe 500 million times to be reasonably sure that we would get this. So it's never going to happen. The sample mean is going to be close to the true mean, much closer than 35,000. Okay, so let's think of this. If x bar is the sample mean for 100 houses, what is the range into which x bar will lie 68% for 68% of all possible samples? So what that's saying is, maybe you recognize the 68% from the empirical rule. Oops, I put the bar on top of the sigma. So sigma x bar. What we're asking here is, what is this interval? It's saying for what interval? Can we say that x bar will lie with 68% probability? As in, for 68% of all the outcomes in our sample space. Of all outcomes. What is an outcome here? An outcome is a certain set of 100 households. For 68% of all outcomes in our sample space. So that reminds me, what is this distribution called? This is the sampling distribution of x bar. Meaning it's the distribution of all possible values of x bar for all possible samples. of size n. Size n equals 100. Okay, so I said all those words, but I didn't really have to write all that. I could have just done the empirical rule. So it's from ux bar minus sigma x bar, which is 72641 minus 6340. 66301. Do it here. 66,301 up to adding 1 sigma the other way. How do I know this? It's because it's a normal distribution. This kind of thing would be true for any normal distribution. 78,981. Okay, so you can see that's a fairly tight range around the mean, and 68% of the time, the survey is going to give us a result in that range. Okay, what if I wanted an even tighter range? I would have to use a larger sample. Okay, so that's the end of the central limit theorem, and let's just summarize the, sometimes we call it CLT for central limit theorem. What it's saying is that sigma of the sample mean is sigma of x divided by the square root of n. It's saying that the mean of the sample mean is the underlying mean, and the main thing, the key thing, is that x bar is a normal distribution. It follows a normal distribution as long as there are two possible cases here, as long as either x itself is normal, which is kind of the easy case, less common, or if n is greater than or equal to 30, i.e. large enough. And some of you who like precision might say, I don't like this large enough business, I want to know. But there is no black and white answer here. It depends on the shape of the original variable. If the original variable is almost normal, then n doesn't have to be very big. But if the original shape is extremely skewed, has very weird outliers, you might need n to be 1,000,000. To bring kind of Jeff Bezos level outlierness, kind of drag him down to the average, n would have to be probably 1,000,000,000. Something like that. Okay. I have to think about that one. In any case, we're going to leave it there. See you in the next video.